All right, so last week we were talking about work energy theorem, okay, where we said that work is a change in mechanical energy, right? For us in Science 10, that means either the kinetic energy of an object is changing or the potential energy of the object is changing, right? So what we have to do is we have to identify from a question which one is changing. Is it potential energy or kinetic energy, right? The way we tell that is we look for what's happening to the object. If the object's height is being changed, then we are changing its potential energy because it's getting further away from the Earth's surface or closer to it, okay? And as a result, that's changing its height, which is part of potential energy. Or its speed could be changing, and speed is part of kinetic energy. So if we see that an object's speed is changing, then we know that the work being done is changing the kinetic energy of the object. So in this question, we have a mail carrier who is taking a package from the 3rd floor of a building to the 10th floor of the building. All right, what kind of energy are they changing about the package? It's potential energy, because it doesn't mention anything about its speed changing, just that it's going to be higher above the ground than it was when we started. All right, so we're going to say that work equals the change in potential energy. Sometimes we have to write force times distance equals that, but not in this case because the question is only asking us to calculate the work. All right, so all I have to do then is say that that means the final potential energy minus the initial potential energy, that'll be the change. Remember, anytime we see delta, it means change. Delta is the triangle. Okay? Whenever we see that, it means final minus initial. In this case, it's final minus initial potential energy. Okay, so further then, we write in the formula for potential energy, which we learned last week is m times g times h, where m is the mass, g is 9.81, and h is the height. Okay, so this will be the final height minus m times g times h initial height. Okay, then we can plug in our numbers. So we're going to have, it's a 10 kilogram package, yeah. Okay, so 10 kilogram package. Okay, actually we don't need the units in there, not for this part anyway. Okay, so 10 times 9.81 times 100 meters, because we went to the 10th floor. So its final height is 100 meters, minus 10 times 9.81 times 30 meters. Okay, everybody with me there? Okay, so we got 100 times 9.81, sorry, not 100, 10 times 9.81 times 100 minus, okay, 10 times 9.81 times 30. All right, so the mail carrier is going to have to do 6,867 joules worth of work in order to carry the package from the 3rd floor to the 10th floor. That is how much its potential energy changes by. Okay. Okay, everybody follow what we did there? Just final minus initial. Okay, I want you guys to see if you can try this one. All right, so I have a bulldozer that's going to do 7,500 joules of work in pushing a truck from a speed of 2 meters per second to an unknown final speed. All right, if the truck has a mass of 2,500 kilograms, what is its final speed? The number in blue here is the actual answer, so you'll know if you did it right if you get that answer. Right? But remember, when we're doing these questions, we want to first identify what kind of energy is changing and then set up our work energy theorem formula. Okay, I'm going to give you guys a couple minutes and see how you do on that one before I go through it. Okay, let's walk through the first couple steps here. First off, what kind of energy is changing about the truck? It's kinetic energy because its speed is changing. All right, so we know right off the bat then that in this case, the work is going to equal the change in the kinetic energy of the truck, which means then that we can write in here that work equals 1/2 mvf squared minus 1/2 mvi squared. Okay, that's what's being set up here. We have an initial kinetic energy and a final kinetic energy. What we don't know is this number. That's the number that we need to find. It wants to know it's the unknown final speed of the truck. I'm going to give you a couple more minutes now, see if you can isolate that and solve for it. All right, so I'm looking for VF. So the first thing I need to do is move this whole term over to this side. Since I'm subtracting that term, can I add that term over to the other side? Okay. So I'm going to have whatever work is done plus the initial kinetic energy, the initial kinetic energy, okay, should equal my final kinetic energy. All right, that should make sense, right? I take what I start with, add in the change, and I should have what I end with. Right? That's what that manipulation is saying. Now, I'm looking for VF. So what do I have to do with the half and the M? Okay, I want to isolate VF. So how do I do that? What do I do with the half and the M? I divide them over to the other side because I'm multiplying them right now. Okay, now they don't cancel. I know there's a half M on the top and a half M on the bottom, but there's another operation up here. All right, that solves for VF squared, but I only want VF, so I need to square root. All right, so I'm going to have that VF equals the square root of the work, which they told me is 7,500 joules. Okay, the question told me how much work was going on, plus 1/2 times the mass, which was 2,500, times the initial speed, which was 2, times 2 squared, right, divided by 1/2 times 2,500. Yeah, so when I do that, I should get VF. Okay, so 7,500 plus 0.5 times 2,500 times 4, that's 2 squared, okay, divided by half of 2,500, so 1.1250. Okay, and then I got to square root that, and I get 3.16 meters per second. Okay. Questions on how that one works? Okay, in terms of the algebra, that's probably one of the tougher ones you would run into. All right, so set of steps to follow when we're doing work energy theorem problems. I would say it is vital that you write these down because they're not in your notes anywhere. Okay, so write these down. If I want to solve a work energy theorem question, the first thing I should do, write out my givens. Okay, whatever the question gives me, write it down because you get a mark for that. Okay, it's an easy mark. All right, so once we've written out our givens, then we want to decide whether we're going to be using work as a change in energy or force times distance as a change in energy. And we'll be able to tell that based on what we were given. Okay, if we were asked to calculate work or we were given the work in joules, then we'll use work as a change in energy. If we were given a force or given a distance and asked to calculate force or something like that, then we'll use the force times distance one. All right. The next step, identify the type of energy being changed. Is it kinetic or potential? And we said the way you check for that is the height changing or the speed changing? Okay, the speed's changing, we're dealing with a change in kinetic. If the height's changing, we're dealing with a change in potential. All right, once we know that, then we'll set up the work energy theorem to solve for whichever one is happening. So we'll say work's a change in energy. Maybe it's force times distance equals final minus initial. And that could mean either, here on the left, kinetic. So we might write force times distance is 1/2 mvf minus 1/2 mbi. Or if it was potential, force times distance is mghf minus mghi. Whichever, okay, we have to decide whether it's kinetic or potential. Okay, either way, it's going to be final minus initial. Okay. And then once we've done that, then we manipulate the equation to solve for whatever we were looking for, just like we did in the last question where we were looking for VF. We moved everything around and isolated it and then solved for it. All right, so those are the steps to solving a work energy theorem problem. Okay. All right, I want you guys to try this one. I've got the answer on there so you can check and see if you did it right. Okay, but I have a person who uses an unknown force to lift a 50 kilogram mass to a height of 1.5 meters. Okay, how much force was used? All right, so write down your givens. Okay, decide what kind of energy is changing. Set it up, manipulate, and solve. All right, give you a few minutes on that one. All right, let's have a look at this one. What kind of energy is changing in this one? Potential energy, right? Okay, but we're looking for how much force was used. Kind of a weird thing with this one. Okay, when we're doing this, what's actually happening is, is that our force times distance is actually, our distance and our height are actually the same number, right? Because it's a distance is a vertical height. So I'm still going to set up my givens here. My mass is 50 kilograms. Okay, we know that G is 9.81 meters per second squared. We know the height is 1.5 meters. That's also the distance over which the force was exerted. Right? If I'm lifting something 1.5 meters, well, then I have to exert the force for 1.5 meters. Everybody follow? If I'm firing something up in the air with a bow and arrow, then that's not true. I would only pull the bow and arrow back this far, and it would shoot the arrow much further into the sky. Okay? But in this case, because I'm lifting it, they're the same number. Okay, so we know that work in this case is the change in potential energy. And since we're asking to find a force, that means I have to use the force times distance version of this. All right, so that's going to be m times g times hf minus m times g times hi. All right, what was my initial height? Yeah, 0. Okay, it doesn't say I lifted it from a height above the ground. I have to assume I lifted it from the ground. So do I have any initial potential energy? None. So I can just get rid of that. All the work done is going to equal the final potential energy here. So I'm looking for the force, so I'm going to divide both sides by d. Okay, and so we're going to have force equals 50 kilograms times 9.81 times 1.5 divided by 1.5. Well, 1.5's cancel, right? And I end up with just 50 times 9.81, which is 190.5. And that would be newtons, okay, the units for force. All right, that's a pretty tricky one. It would be, let's say, if someone had a mass of 50 kilograms, so like an average 15, 16-year-old were to stand on your chest, that's how much force you would feel. Okay. Anybody need that anymore? All right, so let's try this one. We talked about this moving a box up a ramp kind of thing. Okay. Oh shoot, I erased the answer. Try that again without erasing the answer. All right. So I've got a heavy box that's pushed up a hill using a force of 150 newtons. The hill is 25 meters long. Okay. How much higher is the box? At the top of the hill. So all the way from the bottom of the hill to the top of the hill. We're told the force, we're told the distance. We're looking for our final height here. All right, so what kind of energy am I changing in this one? Potential. It says nothing about me speeding the box up, just that I'm pushing it up the ramp. Okay, it doesn't say anything about it going faster. If it's going up a ramp, though, it's getting higher above the ground, so I need to calculate its change in potential energy if I want to figure out how much higher it is, which would be this right here, okay, at the end. Everybody follow? Okay, the length of the ramp is the distance over which I exert this 150 Newton force. All right, so that's my distance and my force that I'm going to use on the other side. All right, so my givens were, okay, that I have a mass of 35 kilograms, a force of 150 newtons, okay, a distance of 25 meters, all right, and I know that G is 9.81. All right, so that means then that I've got work being a change in potential energy. All right, that's going to mean force times distance equals m times g times h final minus m times g times h initial. But where was I at the beginning of this? On the ground, at the bottom of the ramp. so I don't have any initial potential energy, which actually makes the question easier because then I don't have to worry about moving that stuff around. I can just cancel it off. Okay, so I'm looking for my final height. Okay, I'm looking for HF. So to get that, I need to divide both sides by mg so that HF is by itself. All right, so there's my manipulation, FD over mg. So that's going to mean 150 newtons times 25 meters divided by 35 kilograms times 9.81 meters per second squared. Okay, so 150 times 25. Okay, divided by 35 times 9.81. All right, so it ends up 10.9 meters higher than it was at the bottom of the ramp. All right. Everybody all right with how that one worked? That is a very typical work energy theorem question. Okay, like I said, I put one like that on last year's unit exam. So that is exactly the kind of thing I would ask you. Okay, and here's why I would ask you that. It asks you to use this formula. It has no initial energy, which actually makes it a little easier mathematically. Okay, it tells me very quickly whether you understand this concept and not how good you are at algebra. Okay, it's not like a really testing algebra question. It's a do you understand work energy theorem question. Okay, which is what I want to know in the end. Okay, try that one. I know we're going over a lot of examples, but in physics, you've got to practice and be exposed to a lot of different situations in which the concept you're studying can apply. Right? So this is another one. All right, what kind of energy is changing in this question? Kinetic, yeah, because we're speeding it up, right? Right. We have to assume that when a pitcher is holding the ball, its initial speed is 0, right? And he's going to release it at 72.7 meters per second, right? So we're going to be changing the kinetic energy of the baseball here. So our givens are, we have a force of 300 newtons, a distance of 2.2 meters, right? And a final speed of 72.7 meters per second, and an initial speed of 0 meters per second, right? And also a mass of 0.250 kilograms. Okay, so as we said, we're changing the kinetic energy here. So we're going to have work equals the change in kinetic energy. That means force times distance equals 1/2 mvf squared minus 1/2 mvi squared. All right, so you'd get a mark for your givens, and you would get a mark for this step here, identifying what type of energy is changing in the question. Okay, can I eliminate anything from this equation the way I've written it? What's VI? Okay, so what's anything multiplied by VI? 0. So can I take out the 1/2 mvi squared? Yeah, because that whole term is just going to end up being 0, and if I subtract 0, it doesn't change anything. So I'm just going to take that out of there. Right? So you'd probably get some sort of manipulation mark somewhere in here. We're looking for the final speed of the ball, so we would divide both sides by 1/2 of m to get VF by itself. But that's VF squared, and I want VF. So what do I have to do? Square root. Okay. All right. So you'd probably get a mark for that step, and then you get a mark for plugging in your numbers. So we would have 300 times 2.2, so force times distance, divided by 1/2 times the mass, 0.250. Okay. All square rooted should give me VF. All right. So you'd probably get a number there for plugging your numbers in. So we're up to 4 marks, and then getting VF would be our final mark. So 300 times 2.2, there's the work done, okay, divided by 0.125, and then square rooted. Oh, what did I mess up? Oh, I got 22, not 2.2. Start that over again. 300 times 2.2, okay, divided by 0.125, and then square rooted. That's better. 72.7 meters per second. Okay. Last year on the unit exam, I had a question like the ramp in the last question, and I had a question just like this one too. All right, I had one work energy theorem question for each type of energy. So one where potential changed and one where kinetic changed. I did. 0.125 is half of 0.250. When you go 0.5 times 0.25, you get half of that. I just did that in my head. Okay, 0.5 times 0.250 is 0.125. You have to put that part in brackets on the bottom. Like if you're doing that in your calculator, okay, it would look like this. So if you're doing it all in one step, so I'd have second, right, and then I'd have 300 times 2.2 divided by 0.5 times 0.250. Okay, you have to, that's why I do it step by step. That's why I never enter it as one thing. If I make a mistake, I enter the whole thing over again. Right. All right, any other questions on that one? All right, I'm going to give you about a little 5-minute break here. Okay, just kind of stand up, walk around a little bit because you've been working on problems since we started today. And so take a little 5-minute break, and then we'll get into the next thing here. Okay, as always, what's the kind of energy that's changing here? The kinetic energy is changing because we're going from 20 meters per second to 0, right? So that means we know our final energy is, if we're stopping, what's our final kinetic energy? 0. All right, so we know our work being done is going to change our kinetic energy. So that means the force times the distance equals 1/2 mvf squared minus 1/2 mvi squared. And we just said our final is 0 because we're coming to a stop. Oh, sorry, to 6. Sorry. You're right. It's not 0. It's 6. All right, so we have both. 1/2 mvf squared. Sorry. Just assumed it was like that. Okay, so I'm looking for how far it traveled. So I want to find D. What do I have to do with F? Just divide it over to the other side. Whoop. Just divide it over to the other side. So I've got F. Okay. All right, now I can plug in my numbers. All right, so D is going to equal 1/2 times 1,700 kilograms, the mass of the car, times 6 squared, minus 1/2 times 1,700 times 20 squared. All right, that'll get us our change in energy. And it's going to be negative. The car is losing energy here, right? Its final energy is less than its initial. And then we're going to divide that by the force. Now, technically, because the force is opposing, it should also be negative, but it doesn't really matter if you don't remember that or not. Okay, so 10,000 newtons. All right, so we got 0.5 times 1,700 times 6 squared minus 0.5 times 1,700 times 20 squared. All right, so we got a negative number there divided by negative 10,000. And again, it doesn't matter whether you made it negative or not. Okay, if you didn't make it negative, you got negative 30.94. If you did make it negative, you got 30.94. In the end, it asked for distance. Is distance scalar or vector? Scalar. So if it came out negative, you just forget it's negative. It's 30.94 meters. Okay, that's all that matters. Okay, all right. Are we starting to see, like, are these pretty patterned? They're all pretty much the same. Once you learn the pattern, the only thing that's tricky is identifying whether it's kinetic or potential energy that's changing. Once you can figure that out, they're all pretty much the same. Okay. Now, I say that because on your unit exam, you are going to have one of each type of these questions. You're going to have one that has potential and one that has kinetic. Okay. That could be between 10 and 12 marks on your unit exam on this stuff, which is all patterned. If you can remember the pattern, then you can get 10 or 12 marks, okay, on that section of the test. So that's something we definitely want to look at. Yes. Okay, now this is a very typical one as well. So I want you guys to try this one. This is like slingshot, bow and arrow. They're all pretty much the same. Okay, but give this one a try, all right, and see if you can figure it out. Okay, so let's write down our givens on this one here. Okay, so we're firing the slingshot straight upwards in the air. It's drawn back 0.4 meters. What did they give me there? If I'm pulling back a slingshot, okay, I'm using a force over distance. Yeah, that's my distance. So distance is 0.4 meters, okay, and the force is 1,500 newtons. All right, so we got force and distance. Work's definitely being done, and we know that it's going to reach a height of 30 meters. Would that be our initial or final height? Final. That's the height it reaches. Okay, so its final height is 30, and we said just before we started this that we needed to assume our initial height was what? 0. I haven't seen anyone fire a slingshot while floating in the air, right? So we have to assume they were standing on the ground or lying on the ground when they did this. So our initial height is 0 meters. Okay, so what kind of energy is changing in this? Potential, yeah. I mean, kinetic is changing as well, but we're not being asked about that. We're being asked about the change in height here, which is the change in potential energy. So work equals our change in potential energy in this one. That'll be force times distance equals m times g times h final minus m times g times h initial. And how much potential energy can I have if I'm on the ground? None. All right, so that means my initial potential energy is 0. All right, so I'm looking for the mass of the rock. I'm looking for M. So what do I have to do with G and HF? Divide them over to the other side. Okay, that leaves me with M. Then I can plug in my numbers. All right, so I'm going to have 1,500 times the distance, 0.4 meters, divided by 9.81 times 30 meters. Okay, the key to getting this one right is you got to make sure the top and bottom are separated by brackets or by doing them separately. 1,500 times 0.4, okay, gives me that. And I'm going to divide by the bottom, 9.81 times 30. Okay, so I've separated them by brackets, okay, and I'm getting that the final height is 2.04 meters. Okay, meters. Or sorry, not meters. Sorry, 2.04 kilograms. Looking for mass. Sorry. 2.04 kilograms. Okay, again, does that one still kind of fit our formula that we've been doing? Work is a change in energy. Force times distance is equal to final minus initial, and so on and so on. They all set up the same. The first set of steps is the same, regardless of what kind of problem you are dealing with. Okay. All right, in your workbook, there are some problems I want you guys to try. Okay, so you can work through them at your own pace here instead of kind of one at a time like we've been doing. All right, so we need the physics one. All right, I want you guys to try starting here on page 11. Okay, so about halfway down page 11 is where those ones start. Okay, see how you do with those. We'll go over a few of these as need be.